So electromagnetic induction is our last big idea for this unit. And notice what's in the word electromagnetic. I even highlighted it. Electricity and magnetism. Okay? Induction is this idea that you can bring something about indirectly. So the idea is an electric current can indirectly bring about a magnetic field, and a magnetic field can indirectly bring about an electric current. The math can get really nasty and weird and three-dimensional and use vector calculus and whatever, but the basic ideas you can actually do, okay? And that's what we want to hit on, to have a fundamental understanding. So maybe another way to look at this is in terms of induction, is biology. So usually when a woman is pregnant and they're about to have their first child, the first baby, the kid doesn't want to come out. The baby's smart. Hey, it's kind of nice in here. It's warm. I get free food. Actually, you get everything through the umbilical cord. You get food and drink, and that's how you breathe. It's like better than cable TV, 24/7, right? So the kid doesn't want to come out. So then the doctor can induce labor using natural hormones and drugs and things like that. Pitocin, I think is what it's called. So I remember when baby Lau number 1 was born, she didn't want to come out. And when the anesthesiologists and the doctors came in, I want to give them all a big hug, like, thank you. Woo, hallelujah. Life is good, right? So anyway, electromagnetic induction. The first person we give credit to is this Danish scientist. His name was Hans Christian Ørsted. He was a professor, and he discovered accidentally that an electric current produces magnetism. And the way they figured that out is, accidentally, they had a wire set up, and they ran electric current through there, through a battery. They were probably doing like a little physics lecture there. And then nearby they had a compass, and they saw that every time they hooked up the circuit, the compass needle swung, it deflected, showing that an electric current can make a magnetic field. And that's how we made our electromagnet to pick up the paper clips, all that good stuff, right? You just wrap a bunch of wire around nails, you pump current through, got an electromagnet. Now the question is, can magnetism make an electric current? And the answer is it can, but there's always a little but, okay? There's two little tricks to it. And we give credit to two guys. One guy's name is Lenz's law. And then the other guy is a gentleman named Michael Faraday. So Lenz's law simply states, and here's the two key words I want you to take away from today's little mini lecture here. And then we're going to do like a whole bunch of crazy demos. We're going to go nuts, like 15 different demos. The two key words are changing and opposing. And the big idea is you don't get something for nothing, okay? Lenz's law simply states that a changing magnetic field through a circuit, like a coil of wire, will induce an opposing magnetic field from the electric current that flows. And the reason why is why opposing? It's because you have to conserve what we call energy, mechanical energy. You don't get something for nothing, okay? And rather than trying to explain this little crazy diagram, I'm going to show you guys one of the FET simulations and then show you a little crazy demonstration here. So in a generator, how does a generator work, okay? When I turn the crank, inside this crank, there's a what? Oh, I heard it. Good. There is a motor, but what is a motor? You know what's funny? A generator is just a motor in reverse. That's all. You're a little ahead of me. Good job. There's a magnet inside a coil of wire. Okay? So notice, no light coming on my little light bulb here, right? And how come? Because is the magnetic field changing? It's not. You don't get something for nothing. A generator converts mechanical energy, energy of motion, into electrical energy. So the trick is you have to have a changing magnetic field. Wow! And notice if I change it a little bit, I get a little bit of electric current, right? If I change it a lot, I get a lot. Wow! So exciting. Not that exciting. That's okay. But this is a big deal because all of modern life is we can turn this into that and that into this, okay? A motor is just electrical conversion to a mechanical conversion. A generator is just vice versa. So here's why it has to be changing and opposing. The first thing is you can't get something for nothing. Okay, let the last lunch bell go. There we go. Woo. So anyway, if I don't change the magnetic field, I'm not going to get electric current. You can't get something for nothing. Now, if it wasn't opposing, that's the other key word. Here's what would happen. I change the magnetic field a little bit. The changing magnetic field inside the coil makes an electric current. But wait a second. Doesn't an electric current make a magnetic field? It does, right? That's the source of all magnetism. So now an electric current generates a magnetic field. But wait a second. A changing magnetic field makes an electric current. You know what would happen if it didn't generate an opposing field? I would turn the crank a little bit, and then the light bulb would get brighter and brighter and brighter until it blew up in my face. It wouldn't make any sense. You would have infinite free energy. Okay? So the only thing that makes sense is you generate an opposing current that makes an opposing magnetic field. Okay? Your book uses this fancy term called magnetic flux, which is defined as the amount of field lines that flow through a given area, and it's really mathematical. I like to approach it in a conceptual way. Think of it like fishing, okay? All you're trying to do is you spread a net to try to catch those field lines. And if you can catch more fish and catch more changing fish, you'll get more of an electric current there. So the two key words is what when it comes to induction? Changing and what? Opposing. Let's try to visualize it and break it down. The Colorado FET simulation is a good way to see this here. So notice I have a coil of wire, a pickup coil, also an electric guitar, but in this case we're just trying to light up a light bulb, and a magnet. How come I'm not getting any electric current? This stinks, because you have to have what kind of field? Remember? What's the two keywords? Changing, okay? So notice that if I move the magnet in, wow, it changed, right? Then the light bulb goes. Isn't that exciting? Pretend you're excited. So excited. Okay, we'll turn on all these sensors so you can see what's going on, right? So notice that if I change the field, it lights up, right? And notice that when I put it into the coil, the electric current flows down, okay? It flows down. And later on tomorrow we're going to learn what's called the right-hand rule to figure out which way the currents flow. And there's one called the coil rule, where your thumb points in the direction of the field and then your fingers curl in the direction of the current, okay? But anyhow, if I increase the field going in, the current flows downwards, and then if I pull it out where I decrease it, then the current flows the other way. But the point is it's opposing. You see that? So the point is you have to have a changing field and an opposing one to keep the light bulb lit. Now this would be annoying that every time you want to light up a light bulb, you have to keep moving this magnet around. So in real life, we use a generator maybe hooked up to some water falling, like at a waterfall, hydroelectric power, right? Like Niagara Falls, the Hoover Dam. And let me turn on all these sensors so you can see what's going on. Then we can generate a continuing source of alternating current. You see that? Now we could do a lot of weird math. We're going to use common sense. How could I get more power out of my generator here? How about the size of the loop? What will work better, a smaller loop or a bigger loop? What do you think? Okay, well, smaller loop, I'm going to catch less fields or more fields. Looks like less fields, right? So if I have a bigger loop, if I catch more fields, that'll be a bigger change. I'm going to get more power. Make sense? What's another way I could get more power? Can you figure it out? What if I increase the number of loops, right? Then I get even more of a change captured, more fish. I'm catching more fish. Think of it that way, through this loop there. You see that? So it turns out that if this is perpendicular to the changing fields and I have bigger area loop and more loops and a quicker change, I'm going to get a greater source of induced current. Okay? So in some ways, it's kind of common sense, intuitively, in terms of energy conservation. In some ways, it's not, because usually you don't think about it. You just flick a switch, push a button, ring a bell, etc. there. Okay? So in a nutshell, induction, two keywords, changing and opposing. A changing magnetic field will induce an opposing electric current that creates an opposing magnetic field to conserve energy. Got it? So now we're going to go nuts. Whole bunch of demonstrations to help you see how this works.